congratulating Giorgio for his 70th birthday by breaking my shoulder and still coming here. And I didn't do it for Stefano. I was supposed to be in Trieste last week, but I canceled. So you should appreciate that I did not cancel here, but actually the reason is it's not so painful as it used to be. So at these words, Giorgio, congratulations. I hope many, many more years of great science. And I would like to invite Guilhem for the first lecture on phase transitions in inference problems on sparse random graphs.
Thank you.
And you have 45 minutes.
Thank you. So I would like first to thank the organizer for the invitation to talk in this very nice occasion. It's a great pleasure and a great honor for me. I didn't have the opportunity and the chance to collaborate directly with Giorgio, but I mean, I've benefited directly and indirectly from many things he has done, so thanks a lot, Giorgio, and happy birthday once again. So I will present in this talk some results that we have obtained recently with Federico Ricci-Terzanchi and Lanka Zdeborova. So I will continue the line which was started in the first two seminars this morning, so of these inference problems. So maybe most of you are most used to the kind of traditional spin glass or traditional disordered system. So it's very much related, but it's important to keep in mind that in this kind of problem there is, the disorder is generated in a specific way where there is really a signal hidden in the disorder that you have to treat, which makes some, a bit different from maybe the more traditional spin glass problems you have in mind. In any case, what I plan to do is to define two variants of a problem on graphs and on trees, discuss the connection between the two, and then present something which might, at first is a very simple observation on the way to think about this phase transition, and this was already mentioned by Florent, but I will give a little bit more details on this and show, that there are some non-trivial predictions that can be made starting from this observation. So let me start by defining another problem that Florent only mentioned briefly, which is called the stochastic block model. So it's you can view it from different ways. One is that there is something called communities in graphs or in networks, which traduce in a rough way the idea that, for instance, if you think of political blogs or Facebook pages, there are some communities, people that know each other or think in the same way. And you can try to develop algorithms to find these communities, but a priori, you don't know what is the real truth that the algorithm wants to discover. So it's important to have null model where you have put the truth by hand, and so that you can use to test the algorithm. You can also view it from a more formal point of view, that is of random graphs. So it is a way of generating random graphs where first you draw some labels, some colors, some opinions for each of the vertices with this a prior probability, which I will denote eta bar. And then you put edges between these vertices, meaning that people know each other, if you want, with some probabilities that depend on their opinion, on the labels that are put on it with this parameter C. So here, the model is parameterized by the number of different type of opinion, of colors of the vertices, the prior probability on these opinions, and then the symmetry matrix, which tells you, what is the tendency of two people of two given opinions to connect to each other. And the inference problem is that if you are given only the edges between two people, and not the original labels, you want to recover the original labels as much as possible. In the best way that you can do. And here, the idea is that if you know the parameters that generated these graphs, the best you can do is to use Bayes' theorem and to write the posterior probability of the labels given your observations, given the graph. And this enters in the framework that Florent described earlier this morning. So here, in the rest of the talk, I will make a technical assumption which is written, in this way, but which essentially tells that if you just look at the number of neighbors of a vertex, or the number of friends some people have, this does not give you any information of his opinion, of his color, of his hidden label. Okay, so it's a balanced assumption. There is one way to verify this hypothesis, but which is a further restriction of the model, is just to say that the Q possible labels are equiprobable a priori, and that this parameter of the connectivity matrix only depends whether the two people are of the same opinion or of different opinion. Okay, so it's a very symmetric subspace of parameters which verify this balance assumption. And then it's convenient to parameterize then the model with C, which will give the average degree of the graph, so the average number of neighbors of one individual. And this parameter theta with, some rescaling, which is, useful to have simple formula, but essentially which tells that if this parameter theta is equal to 0, then there is no community at all, because you have exactly the same probability to connect to someone of your opinion and to someone of another opinion, so there is no information at all in the graph you are generating in this way. And if it's positive, you have tendency to connect more to people of the same opinion as you, and negative, the opposite way around. Okay, so if you think in terms of information retrieval, the signal-to-noise ratio, the amount of signals that you can exploit, you can view it either as the absolute value of this parameter theta for a given average degree, or vice versa. And in the following, I will discuss what happens when you change the signal-to-noise ratio and what happens to the accuracy of what you can get from the graph in terms of the original problem. So I don't want to give a precise definition. There are some technical subtleties, but the idea is how much you can recover from the hidden label from the graph using an estimator based on the graph. And this is the accuracy. Okay. Okay, so this problem has a long history. I will just mention one work of Florent Lanka, Aurélien Dessel, and Chris Moore, which, who studied this model with statistical mechanics method in the case of this symmetric problem, and which, emphasized the existence of two types of scenario. So depending on the number of communities or number of possible opinions, when it is small, these curves, which represent the accuracy as a function of the signal-to-noise ratio, have this shape. So there is a phase at low signal-to-noise ratio where it's impossible to get any non-trivial information on the hidden labels. Whereas if you increase the signal-to-noise ratio, the accuracy increases continuously. And not only it increases continuously, but what you can get with computational facilities as large as you want is actually something that you can reach in a polynomial time with simple algorithm of the type of belief propagation or approximate message passing as Florent described. On the contrary, if you go to a large number of communities, you have a discontinuous phase transition, where the best you can do differs from what you can do efficiently in a phase which is called this art phase. And and so there is this intermediate regime between the phase where what you can do efficiently matches the best you can do with an exponential amount of time, and the impossible phase where whatever you do, you will not get any non-trivial information. Okay, and as Florent already said, this is a pattern which occurred in a wealth of very different information theoretic problems. Okay, and so this I will call in the following the threshold where you start to get something non-trivial from the from the efficient algorithm, the Kesten-Stigum transition, and instead the optimal one is has a discontinuity at the so-called information theoretic transition. Okay, so I mean, I'm sure you have guessed, you have noticed that Q equals 4 is not treated here, and that I will come back on this. That will be one of the non-trivial results I want to present at the end. So there has been, I mean, a lot of work before and also after this this paper, and this a lot of part of these results were later proven rigorously, and okay, as we have already said, there are a lot of other problems which exhibit these two scenarios, and also I will come back on something which is called the planted constraint satisfaction problem. So you might know constraint satisfaction problem like coloring or K-SAT problem, where you have a set of variables which are subjected to some constraints, discrete constraints. And the planted version of them is that where you first choose a configuration and you impose that this is a solution of the problem you are constructing. Okay, so you are extracting constraints which must satisfy this hidden assignment. And it's very much related to what I presented on the stochastic block model. Okay, so let me move to a slight variation on this problem, which is called the tree reconstruction problem. So here is the setting. I have a tree, so an acyclic graph. I consider it to be rooted at this point. Okay, and I use it as an information channel in the following way. I am first choosing some label in a discrete set with this a priori probability eta bar of the root. And then I'm sending it through this tree, which means that on all the edges, I'm forwarding the information on the root, but with some noise. Okay, so there is some probability transition that the son of the root gets a corrupted version of the information on the root itself. And this continues on each branches. Every time the sons get a noisy information about their father or mother, if you prefer. And the question is the following. If you are given the observation on all of the leaves of the graph, so on a faraway boundary of the original root, can you tell something about what happened inside, and in particular, what was the value of the root, if you are just given the observation on the leaves? Okay? And, okay, so here, the problem as it's defined on a tree is, I mean, at least there is a formal way of thinking about it, is once again to write the posterior distribution thanks to Bayes' theorem, the posterior distribution of the root given the observation. And as this is a tree, this has a simple structure because a tree is recursive by nature. So you can write exact recursive equations that will allow you to compute exactly the probability that the root was in a certain value given the observation. Okay? But now the question is, if I send this to a very large, I mean, if I send the leaves to a very large distance, does this keep some information? Okay, so to answer this question, one can introduce the distribution of this posterior probability with respect to the broadcast process and measure how far it is from the prior distribution, which means no information at all. So I'm not going to enter into the technical details. I just want to state that, I mean, it's not a very complicated computation to show that this kind of distribution obeys some recursion, some I mean, induction formula with respect to the depth of the tree. Okay? So you have, at the end, you end up with a recursion as a function of the depth of the tree, where the unknown is the probability distribution. Okay, and okay, one possible way of writing this is schematized here, and it turns out that this actually makes a connection with the 1RSB, one step of replicative symmetry breaking formalism with the Parisi parameter m equals to 1. Okay, for those who know this these technical details. And an important point here is that the starting point of this recursion, which means for a tree of depth 0, I mean, it's just that you know exactly what is the value of the root because it coincides with the leaf. Okay, so in technical words, you have just a sum of Dirac delta on the exact observation for this starting point. There is actually, I mean, a reformulation of the question that I ask: is there some information flowing from the root to the leaf? I mean, it's precisely whether after a long, I mean, you iterate this recursion for many times. Do you flow towards the trivial fixed point, which just says that you know the prior probability, or do you get a non-trivial distribution which captures the correlation between the root on the leaves? And there is actually a variant which will be useful in the following, which is called the robust reconstruction. Whereas, I mean, here you are, I mean, the game is even harder because instead of observing all the labels on the leaves, you are only given a fraction epsilon of them. Okay? So you have much less information, but still you are asked to reconstruct the value of the root. And so, and technically, this is just a different initial condition parameterized by this parameter epsilon. And the worst you can do is to say, okay, I will only give you epsilon equals to 0, so not equal to 0, but going to 0 after the limit of depth of infinitely deep trees. Okay, so that's called the robust variant of the reconstruction problem. Okay, so I presented two versions of the problem which had some common elements. There is this eta bar in both of them. But actually, it was not the same. I mean, in one case, the problem was on a random graph. In the second version, it was on a tree. So the connection between the two is based on the observation that if you look at the original problem, the stochastic block model, and if you look at the random graph it generates, and if you look at it locally, in the sense that you pick one of the vertices at random, and you explore it, following its edges, up to a certain distance. And you do this, if you do this in the thermodynamic limit with this distance which is fixed, what you will see is exactly a Galton-Watson tree, which is a tree where each individual has a number of descendants, which is a random variable with a Poisson distribution. But not only that, if you also look at the labels, you will see exactly the labels broadcasted in the way I described in the second problem. So locally, the two versions of the problems are exactly the same. So globally, the connection is much more subtle because in the graph, there are big loops that you have not in the tree. And also because on the tree problem, I told you that you are given some observation of the labels, whereas in the original graph problem, you have no observation at all to start with. Okay, so this makes the connection much more subtle, but at the end, the conjectures that arise naturally following the cavity or replica method are the two following. Is that if you study the problem on the tree, with this robust reconstruction initialization, so with an infinitesimal amount of information, what this will give you is precisely the accuracy or amount of information that you can reach easily with a simple algorithm for the graph problem. Okay? And it also gives a free entropy, so the replication symmetric free entropy version, I mean, of what Florent presented on several examples, that if you take the maximum or minimum, depending on the signs as usual, this will give you the best that you could do with in infinite time. So it really gives you the mutual information between the graph and the labels that you can get. Okay. So now we have this mean field equation on some order parameters, and they have phase transition. So let's take a look back at this at the two phase diagrams I presented in the beginning. But now these are drawn in a slightly different way, where they are in black and white. But also there are solid and dashed line, which represent stable or unstable branches of the trivial fixed point. Okay? So what you see here is that at this phase transition, there is, the trivial fixed point, which is stable at low signal-to-noise ratio, becomes unstable at high signal-to-noise ratio, and there is a continuous birth of a non-trivial line, which here is correspond to the non-trivial accuracy and the best that you can do. Here, there is also a bifurcation at this Kesten-Stigum point, but the difference is that instead of the birth of a stable branch, you have the death, if you look at increasing signal-to-noise ratio, of an unstable branch, okay, which had a spinodal point before. Okay, that's where the two differences come from. And the information theoretic line, transition in this case, corresponds to a first-order transition to a crossing of two free entropies when you have two non-trivial local minima of the free entropy, if you want. Okay, but that's a simple observation. But now, if you think in these terms, it's easy to construct, or at least to imagine much more complicated bifurcation diagrams. You could just add spinodals, other jumps, and so on and so forth, and other branches. I think that the two following, in order of increasing perversity, will be these two ones, where the branch which the stable branch which is created at this instability of the trivial fixed point, which represents the no information at all, it is created continuously, but it itself undergoes a bifurcation at a later point. Okay, so there is again a spinodal for the high accuracy branch, and if you now think also in terms of where are the phase transition for the crossing of the corresponding free entropies, you realize that there are two new scenarios that appear naturally, which are the following. So here, instead of the impossible, hard, easy phase, I introduce a new term, which is called the hybrid hard phase, which is defined as the following. So it's a little bit easy and a little bit hard, depending on what your question is. So in this intermediate difficulty phase, it is easy to have an accuracy which is better than just the prior information. So which is already a non-trivial information on the hidden signal. But it's hard in the sense that what you can achieve with polynomial time or message passing algorithm is strictly lower than the information theoretical optimal accuracy that you should get. Okay, so that's why it has components of both easy and hard phase. And depending on the location of these two phase transitions, there can be a succession of impossible, easy, hybrid phase, and easy again, or a really hard phase where the efficiently achievable accuracy is strictly 0, and then this hybrid phase, and then again. Okay, so you might think that this is just speculation, which is not very useful. Actually, this kind of phase diagram were already observed, in particular in the works of Thibault Le Sieur with Florent and Lanka in some dense problems, so in particular matrix factorization with some prior. And I will argue in the following that this actually was missed in some previous works on planted constraint satisfaction problems. So I think it's important to have in mind that these two universal scenarios are not, of course, completely universal. Okay, so now let me come to more quantitative messages and the computation. So, as I said, I mean, it's useful to think in terms of this bifurcation. So let's do a very simple case first. So if you had some recursions in this way, where the order parameter is just a positive real, just a scalar, then it is very easy to understand what happens to the trivial fixed point. Well, here is, let me assume that for all parameters, 0 is a fixed point. So obviously what you have to do to understand the phase diagram of the problem is just to expand this around 0, and then you have coefficients, okay? And you will see, I mean, I'm sure that you see easily that if you look first at the linear coefficient, this will give you the stability. Okay, so the point where this coefficient is equal to 1 gives you the location of this stable to unstable bifurcation for the trivial fixed point. And you will see also easily that if you look now at the second order, the term of the second order expansion, depending on this sign, you will have the two main possible behavior, that is either the birth of a continuous branch or the death of a the birth of a stable branch or the death of an unstable branch. And if you play with also the third order expansion, you can also, I mean, in cases where all the terms are of the same order, so close to a three critical point, you can also describe the next order in this bifurcation expansion. Okay, so this is, I mean, just Taylor expansion if the order parameter is a scalar. But as I said, for this problem I defined at the beginning, well, this is a functional order parameter, so it seems more difficult to perform such a bifurcation analysis. So it turns out that, yes, it's more difficult, but it's not impossible. And the idea is that the bifurcation is with respect to a trivial fixed point, so just a Dirac measure. So when close to the bifurcation, what will happen is that this unknown functional order parameter will have small moments. And by chance, they are organized in a hierarchical way, and that you can cut just by concentrating on the lowest order moments, and so that you can close this infinite dimensional problem just on a finite number of unknowns. Okay, so that's what we have done for this family of problems I introduced at the beginning. So I mean, it's not important. Don't look at all the details. I just want to show you the structure of the problem. So here, for the order parameter is this Q by Q matrix, which is the second order moment of the unknown functional parameters. And here is the equivalent of the first two orders of the scalar expansion. So here you see this A hat is some linearly transformed version of the order parameter A, where appears the parameters of the model, the prior distribution and the connectivity matrix. And here is the form of the second order term, so the equivalent of the second derivative of in the scalar case, and the equivalent of the third order derivative. I mean, you can still put it on a slide, but with slightly smaller fonts. But at least in principle, you can. I mean, not only in principle, you can get the expression of this. So why is this interesting, and what are the applications of this expansion on concrete problems? So I will give 4 examples now. So the first one is the problem of this stochastic block model. So this graph problem where I have two possible labels, so two hidden communities, but which a priori are not of the same size. But still, the connection probability are such that just the degree is not in information. So it's asymmetric in size, but balanced in terms of the degrees. And in terms of the reconstruction problem, what was known for a long time is that the transition is continuous. So in these terms, the Kesten-Stigum bound is tight for small asymmetry, where the two groups are essentially of the same size, and it was not at at large enough asymmetries. And what the expansion I just presented leads to at the second order is precisely whether, depending on the parameter of the model, the slope of the non-trivial branch is on one side, on the other side, and that's precisely what decided between these two. And what comes out of this expansion is a value 1 over square root of 3 of this asymmetry parameter that was not known before, and actually that appeared in another paper simultaneously while we were finishing this one. And okay, besides the value of this number, what is interesting is that it's completely independent of the degree distribution for the tree problem, and which explain why exactly the same value was already found in a fully connected or dense version of these problems. So, as I said, the second order expansion give you this critical parameter for the transition from continuous to discontinuous. But as I showed, we also have the third order expansion, and the third order expansion allows also to make some quantitative expansion on how discontinuous it is close to this critical asymmetry. So these are the results of numerical estimation of the threshold. So it's as a function of the asymmetry. And here it's the signal-to-noise ratio rescaled in such a way that the Kesten-Stigum transition, the continuous one, is at 1 precisely. So for smaller value of the asymmetry, you have precisely this continuous transition here. And this shows that indeed for larger asymmetry, we find a discontinuous transition before. And as I said, with the third order expansion, we have some analytical expansions, which are these lines for the behavior close to the critical asymmetry, and which are in good agreement with these numerical results. Okay, so the second model on which we applied this expansion is the one I said was missing in one of the first slides, which is this case of the symmetric block model, stochastic block model, with exactly 4 colors or 4 communities. So actually, this was a bit opened, a bit more difficult to treat, precisely because the second order expansion, if you want, for q equals 4 is exactly equal to 0. So if you want to say something that you really need to compute the third order expansion, that was one of the motivations for this computation. And well, plugging the precise force on the symmetric block model, you find an expression, okay, which is not very illuminating here, which depends on the degree distribution of the problem. And what you can get easily from at this point is the following fact, so that in the assortative case or ferromagnetic case, if you want, for q equals 4 and every degree distribution, the transition is always continuous, so it's more like q equals 2 or 3, whereas in the disassortative case, or anti-ferromagnetic one, you find that there is a condition on the degree distribution that separates the two. And in particular, for Poisson degree distribution, you have a critical value of the degree, which separates continuous from a discontinuous behavior. And that, clarifies some things which were not seen before in several papers. So here is a numerical confirmation of this fact. So here I have the, again, the signal-to-noise ratio rescaled in such a way that the continuous transition would occur at this point. And with the rescaling, which can be extracted from the form of the analytical expansion, this is the point where this should go to 0, so to 1, and go from here discontinuous to continuous at higher degrees. Okay, so now the third application, which also clarifies some things which were wrongly seen in previous papers. So it's not exactly the framework I have defined at the beginning, but it's a slight variant. So with this planted constraint satisfaction problem. So now imagine Ising spins, and that you first draw planted hidden configurations uniformly at random. And then you put some constraints which be on k variables, with some probabilities that just depend on the sum of the spins on which you want to put them. And with just some technical assumption on this, what comes out from this analytical expansion is that the transition is always that there is a birth of a continuous, of a stable branch. Okay, in other words, these three scenarios that I've presented before are possible, but the one which seemed most natural, so this of discontinuous phase transition, and which actually was seen in numerical simulation in previous papers, is impossible. And because, I mean, but of course that was the most natural one to expect, and it would have been very difficult to see it numerically, because there is this small branch. I mean, it's very small. Okay, so if you don't know from analytical computation that it has to be here, it's very easy to miss it numerically. Okay.
Yep.
Yeah. No, I'm done actually. So the last thing I want to mention is the following. So, as we have seen, depending on the number of communities and the symmetry between the communities, you can have different scenarios. Okay, so now if you think of the stochastic block model, it's defined in terms of a probability distribution on Q labels and a matrix, a Q by Q matrix. So it's clear that, and what was studied at the beginning was just the most symmetric case. But it's clear that you can, it's a huge space of parameters, so you can imagine that you will find all kind of bifurcation diagrams and all kind of phase transition in the most generic case. But it's also impossible to explore it in a systematic way. So what we have done is, to break this symmetry in the simplest way. So considering that the Q opinions are subdivided in two subgroups of opinions, if you want, and keep the symmetry as much as possible inside these two blocks. And again, one can apply this formalism. And what is interesting is that already with this symmetry breaking, not replica, but symmetry breaking pattern, it has to exhibit this hybrid phase for some choice of the parameter. So it's not that exotic, even with this kind of model, you can find it. Okay, so to summarize, well, I've presented these two variants of the problem on stochastic block model on graphs and the tree reconstruction, explain a little bit the connection between the two. And the two main messages that I try to convey is that there is indeed some kind of universality for these impossible easy scenarios or impossible hard easy scenarios, but one should keep in mind that these are obviously only the simplest of the scenarios, and that in some not so exotic cases, more complicated phase diagram can occur, and that it's possible to do analytic expansions to classify these cases. And I thank you for your attention.
Thank you very much, Guilhem, for a very clear lecture. We have a few minutes for questions. Giorgio.
Suppose that you try to do the reconstruction using a wrong value of Q, which may be higher or smaller than the true value. What happens?
Okay, so I mean Q. I don't know if it's for the graph model. Okay, for the graph model, it's true. So I think that Florent and Lanka in their original papers they have studied this because indeed a priori, I mean in real applications you don't know the value of Q. So there is one systematic way to answer this. I think is you try with different Q. And you take the one which takes the higher, which gives you the lower free energy, if you want. So you do some sort of maximum likelihood on this. That's one possible way. So actually, there are also a priori very different methods, which are more spectral methods, and not on the natural adjacency matrix, but on the non-backtracking matrix constructed from the graph. And these have the advantage to be agnostic on the parameters. And here, at least in matrices generated from in graphs generated from the stochastic block model, you can read the value of Q from the structure of the eigenvalues, which goes out from the bulk. So in this case, you don't have to use a prior information on Q.
Okay, any further questions or remarks? Yes, please.
Yeah, so in many phase transitions, it was possible to identify underlying percolation transitions. Is this for this type of phase transition also possible or has been done? So maybe you identify growing clusters of variables where you know whether they are in the same or in different groups. And this percolates at the phase transition.
So there is one question that can be interpreted in terms of I would say, closer to percolation phase transition. Is suppose that you ask that not only you want to know, in the tree problem, not only you want to know the root with a better probability than just the prior, but suppose that you ask whether you are able to say the color of the root without probability of error. I mean, with an exact accuracy. And then this can occur in some for some choice of the parameters, and it occurs through a percolation of frozen variables. Okay, so things in terms of colorings. If you see on the neighborhood of a variable all the colors except one, you know that the father was of the colors that you have not here. And if this percolates inside the tree, then the root is also perfectly reconstructible. That's the only example where I can think of a real direct percolation interpretation, but there might be others, I don't know.
Go ahead.
In your tree reconstruction problem, you have, let's say, eta goes to eta prime on the left, and eta goes to eta prime prime on the right. If instead the branching was collective, that eta becomes eta prime prime, then it's related to a problem in the structure of the syntax of language, as we discussed. Do you think that you can do anything in that case?
So, I mean, said with this level of generality, my answer will be no, because I mean, as soon as you start to induce correlation between the branches, then it's not a tree anymore. You have interactions everywhere. So, I mean, this structure completely breaks down. And you can say that there are some, okay, here I draw the tree, but if you draw an hypertree where edges go to k-1 variables, then the k-1 variables are correlated between themselves. Okay, so there is some local level of correlation that can be handled in this way. If you allow for arbitrary correlation between all the sons, well, no, I don't know what to say. But I mean, partial correlations can be handled at the price of creating larger variables.
Okay, if there are no further questions, then thank you very much for this lecture and for the answers. And let me invite Martin Wade to show us that all models are wrong, I'm sure, including yours, right? All models are wrong, including yours, I hope, right?